So yes, my name is Lucia Lopez, and I did my MGST capstone project on assessing deoxygenation in the Gulf of Mexico through interpolation and 3D modeling. So a little bit about the reason why I chose this topic is it's been a prevalent concern in environmental research. Some environmental research has said that the oxygen levels of the ocean has decreased about 1 gigaton for each year. And then ocean model simulations predict a decline in dissolved oxygen inventory of the global ocean of 1 to 7% by the year 2100. And it's very severe in coastal locations within a 30-kilometer band of the coast. So here is a map I made of global eutrophication and hypoxic sites. Eutrophication is the excess nutrients into coastal waters, mainly from anthropogenic activity due to agricultural runoff from that phosphates, phosphorus, nitrates, they get into the coastal water, upsets the biological balance and causes deoxygenation. So as you can see, it's very prevalent in coastal regions. And so why did I choose the Gulf of Mexico? Well, it has persistent hypoxia in the Louisiana and Texas shelf. So it's one of the most extensive areas of a dead zone. And the 5-year average size of hypoxia in the Gulf of Mexico is about 10,500 square kilometers. And it is one of the largest human-caused areas of bottom water oxygen deficiency. So here is my research site. I chose oxygen measurements about 200 miles south of the coast of Louisiana. And one thing I really like about this map is the bathymetry, which really shows how deep the ocean can get as you move away from the shelf. So my outline of what is to come, I'm going to talk about the methodology, data acquisition, preparation, 3D views, geoprocessing plan, mine analysis, looking at the distribution of the data, which you always have to do when you're doing statistical analysis, data transformations, the relationship between oxygen and depth, and running the different models and comparing them, and then taking the best performing model, taking those prediction outputs, looking at standard errors and 3D visualizations. So my data came from the World Ocean Database. It's part of the National Centers of Environmental Institute. They have data spanning back from Captain Cook's 1772 voyage, and they are the largest repository of quality controlled publicly available ocean data. My data came from profiling float data. They can collect data in multiple methods, but a profiling float is an autonomous vehicle that takes data at a vertical measurement. So it came in this format on the left, which is not very tabular or conducive for the GIS environment. And I had to take it and put it into something that was easy to be read. So you have the longitude, latitude. My data came from 2022 and 2023, and you have to make the elevation negative. So for the GIS to register that it's below sea level. And then a lot of the literature I read talked about hypoxia in milligrams per liters. However, they collect data in micromoles per kilogram. So I had to convert that, or I chose to convert it rather. So you take the micromole value, multiply it by the molar mass of oxygen, which is 32, and divide by 1,000. So this is just the general 3D view of a subset of the points. What I really like about this picture is the bathymetry. It's very interesting, and you can kind of see how oxygen can vary at different elevations. And here is another view, 3 different views of the data. This is the entire data set. I had about 1,600 points. And the first map frame is looking east to west, and the second one is looking south to north, and the last one is looking west to east. So you can really get a sense of what it looks like at all these different angles. That's the real purpose of this image. So looking at the relationship between oxygen and depth, you can see that above 200 meters, oxygen is there's more oxygen. And then as you get to 400 meters, it starts to decrease, or it gets to its lowest point there. And as you get even lower in depth, oxygen increases once again. And that's mechanisms of the oceans that I can touch on later. So distributions of the oxygen data, this has no data transformation. And as you can see, my data that I sourced was very multimodal. We have 3 distinct peaks, and this is not preferred when working with interpolation. Interpolation really does work best when you have normally distributed data. But as you can see, when you're working with real-time, real-world data, not everything is perfect. So a lot of scientists will apply data transformations. It's a mathematical operation to your data points, your measured values, to try and achieve normal distribution. The square root here, which I applied, did not work. We still have multimodal skewed 3 peaks, and the same with the logarithmic. So because of this, in running the interpolation tool, the empirical Bayesian kriging, I wasn't sure what kind of transformation to use, or if it needed a transformation at all. So I decided to run 3 different models, one with no transformation and no vertical trend removal, and then one with an empirical and one with a logarithm. And the vertical trend removal, this is talking about the fact that for a lot of 3D data, your data will change quicker vertically than it will horizontally. And a very good example of this is pressure. If you've ever swam to the very deep part of a swimming pool and you can feel it on your head, and it changes very quickly. So the tool only allows you to apply a vertical trend removal if you're using empirical or logarithm data transformations. So summary statistics for statistical prediction models, the ones for the empirical Bayesian kriging pertaining mostly to standard errors and errors, different types of errors. So I followed the guidance rules. For example, the mean error should be as close to 0 as possible. And I assessed those values for every single model. And the one that was as close to 0 as possible, I highlighted it in green. And the model with the most highlighted green values was the best performing model. So the first prediction, no transformations and no trend removal, was the best performing, had the lowest mean error. The root mean square error was closest to 1, which is ideal. And the average standard error was the smallest out of the 3 as well. But I will say that overall, none of the models really predicted very well. And a good indicator of this is that the 90% and 95th% intervals are supposed to be as close to 90 and 95 respectively, and none of the models really got as very close to 90 or 95. So, but overall, prediction 1 was the best performing one. So taking prediction 1, you're able to, in the 3D output of the empirical Bayesian kriging, take different depths and export those depths, those predictions as contours at different depths. And so I made this map that kind of shows the gradual change in oxygen concentration. At 63 meters, oxygen begins to decrease. It's at its lowest at 525 meters, and it rises again at 1,185. And I wanted to look at the standard errors. You can change the symbology on the output file to show standard errors. And so standard errors are lowest at locations closest to known data points. And this is really intrinsic to spatial autocorrelation, where data points that are closer together are going to be more alike. And so therefore the model in predicting locations that, predicting values at unknown locations are able to have more confidence when the data points are closer together. And so these standard errors are actually as rasters as opposed to the other one was contours. So that's why they look a little bit different, but they are also showing standard errors at depths of 261 meters, 723, and 1,185. And the big takeaway again is that standard errors are lowest closest to known data points and begin to have more error as you move away. And here's another visualization of standard errors. And so you can see from the regression line that the points that are very close to the regression line have less error for those measured values, and the ones that are further away have more error. And if you look at the measured values, 4.3 to 5.8, where those points are very over predicted or have more error, and then 5.3 or 5.5 to 5.8, they are also very far away from the regression line and have more error. That's because the original distribution of the data, you have less data points for those values. And so when there's less data points, there's more error that's being introduced. It doesn't have as many data points to make these predictions off of. And here is a little video of the, you can create a video. This is a nifty skill that I learned to show the oxygen prediction contours at different depths as you go all the way to the bottom. And so the top layer of the ocean has more oxygen because it is mixing with the atmospheric gases, and it's also, there's photosynthesis that's occurring. And then as you get to the oxygen minimum zone, which is at 100 meters to 1,500 meters, it's also called the mesopelagic zone. And the reason why it's very low there is because it's not mixing with atmospheric gases. There's no photosynthesis. And also there's organisms that are consuming organic material, and they also, or decomposing organic material, and they consume oxygen in that process for their metabolic processes to achieve cellular division. So they're eating up a lot of the oxygen there. And then as you can see, oxygen increases at the bottom again. This is because the water at the very bottom is very cold, and oxygen is more soluble in cold water. So the cold water can hold more oxygen. And also there's less circulation going on. So none of that oxygen is being pushed up to the other depths above. So when you create a 3D output in ArcGIS Pro with a 3D tool, you can export it to something called a voxel layer. And a voxel layer is a multidimensional visualization of data. And it looks, right now, this is the initial view. It looks just like the video I just showed you. But what voxel layers allow you to do is to create something called slices. So if you just want to look at a specific portion of your data, kind of sequester it from the rest of the data, you can do that using slices. Or you can look at section surfaces. These are two-sided horizontal vertical sections of the data. And this is really useful if you're trying to look at the vertical water column and inspect something. And then you can also look at isosurfaces, and isosurfaces are showing two different depths that are displaying the same measured values. So you have the top one around 6.13 and the bottom depth around 6.13 milligrams per liter. And so in summary, we learned that deoxygenation of the world's oceans is a rising environmental concern, and the Gulf of Mexico has experienced a lot of these persistent coastal hypoxic events. My main intentions were to source my own data, get familiar with statistical analysis in the study to assess the conditions of the study area, and then also really using 3D visualization and voxel layers to become familiar with these capabilities in ArcGIS Pro. And the model with no data transformations or vertical trend removals had the highest performance. So that concludes my presentation. What questions do you guys have?